Alright, so this is going to be a fairly short video, as my videos go. So we're going to talk about Newton's 3 laws of motion and how those kind of play out. And then this is a lead-in into this assignment 4.1. This is forces. We don't need no sneaking forces. So if you're in class on Thursday, which is tomorrow, you're going to get this assignment and it's going to be due on Monday because you guys are going to be doing the lab. If you're on my Friday group, I already sent it to you, so you need to work on this tomorrow, which is Thursday, because it's going to be due on Monday as well. So both of you, the assignment's going to be due on Monday. So if you're on the Thursday group, watch. If you're on my Thursday group, you're going to get this on Thursday. If you're on my Friday group, I've already sent it to you. You're going to watch this video on Thursday, so you can work on that and then be ready to go. So let's talk about Newton's 3 laws of motion. So the first law is law of inertia. Okay, so that all that basically means is that the more stuff that you have, the harder it is to get it to move. But once you get it moving, it's harder to stop it. So if I take Hank the bowling ball, because Hank has a lot of stuff in it, Hank has a lot of inertia. Okay, so it's very hard to get Hank to move. But once you get Hank moving, it's hard to stop it. Now, listen to me. The only thing that affects inertia is mass, okay? Not weight, okay? It's related to it. It's not how fast it's going, it's mass. So, Hank has a certain mass that's measured in kilograms. If I'm on the moon and I try and make Hank move, it's going to take the exact same force to make Hank move horizontally. Because gravity is acting down, but I'm talking about a horizontal motion. Now, obviously, if I'm on the Earth, it's going to be harder to lift Hank up than it is on the moon, because, and we'll get into this gravity mafia later. So the gravity mafia on Earth is a lot stronger than the gravity mafia on the moon, because the Earth is a bigger mass, or has a greater gravitational pull. So, in terms of just inertia, the only thing, listen to me, the only thing that affects inertia is mass. So if I'm on the Earth, and if I'm on the moon, Hank has the exact same inertia because Hank has the exact same mass. Now, Hank weighs a lot more on the Earth than he does on the moon, and that's one of the calculations you're going to do on your assignment. So that leads us to the second law. And the second law of that is F equals ma. Now, if you're talking about what something weighs, and in a physics class, weight means a gravitational pull. So Fg, which is your gravitational pull, is mg. And this is not mass times gravity, okay? This is mass times your gravitational acceleration. Little g is not gravity, okay? Gravity creates that acceleration. So, remember, if you have, let's say for example, Hank has a mass of 10 kilograms, okay? And we multiply that by 9.8 meters per second squared, we're going to get 98 newtons. So, there's two ways you can determine how much something weighs. If you know the mass, multiply that by 9.8 meters per second squared, there's your weight. The other option is that you take a scale like this, okay? And if I want to know how much this block weighs, I give that a lift. I get 3.88 newtons. So depending upon what you have, okay? Depending upon what you have, you can either multiply the mass times 9.8 meters per second squared, or take a Newton scale. Now the third one is equal and opposite forces. For every force, listen to me, for every force there is an equal and opposite force. So let's talk about some common misconceptions about this. If I take this block of wood and I pull it along at a constant velocity, my force applied going this way is exactly balancing out the frictional force going this way. But that is not Newton's third law. Okay? This is just saying, oh, we're maintaining at a constant velocity. Where Newton's third law plays in is when I pull on the hook, I'm exerting a force on the hook, and the hook is exerting an equal and opposite force back on me. We say that the forces are coupled. Gravity is pulling down, the earth is pulling down on the block, okay? The earth, or the block, is pulling up on the earth. That's a set of equal and opposite forces, which is what we call contact forces. If I drop the block, okay, the block begins to accelerate downward because of the fact that the earth is pulling down on the block. Guess what? The block is also pulling up on the earth because for every force there is an equal and opposite force, okay? So, when you talk about force applied balancing out force friction, that is not Newton's third law. Newton's third law applies where those forces are in contact with each other, or you have a situation where it's a force at a distance. So, here's our Earth, and we have this moon that's in orbit around us. Yes, the Earth is pulling in on the moon. That's what allows it to orbit. But guess what? The moon is pulling out on the Earth with the exact same amount of force. An electron goes around a proton. The electron is pulled towards the proton because they have opposite charges. Guess what? The proton is pulled towards the electron with that same amount of equal and opposite force. Okay? Do not overthink this. I hit down on the table. I exert a downward force on the table exerts an equal and opposite force on me. Don't overthink this. Okay. Now, when you talk about observed motion, okay, this is one of the questions on your assignment. Imagine that I'm in a jet plane, right? And the plane takes off. Okay, so imagine we're in a jet plane and you're looking at me and plane takes off. So here's what you want to look at. My body, because it has mass, and probably more than it should, need to lay off the quarter pounders a little bit, but we'll get to that later. My body wants to remain at rest. So the chair is exerting a forward force on me. Okay, it's going this way. My body wants to remain at rest. Now what everybody says is that, oh, I'm being pushed back into the chair. Well, there's no force in front of you pushing you back into the chair. You just want to remain at rest. So the chair exerts a force on you going forward. You exert an equal and opposite force back on the chair. That's what you feel. There's nothing in front of you that's exerting this invisible force to push you in that direction. That's not what is happening. Okay, so that's going to be one of the questions on your assignment. When you get to question number 5, okay, up here at the top. And by the way, do not answer anything on this sheet. Do not answer a single multiple choice. I am not going to grade anything on here. Everything gets answered on another sheet of paper. Quick review also. Draw a line. Your answers go here. Your work goes here. Leave spaces, okay? Like for example, when you get to like number 2, there's questions A, B, and C. Put your answer to A here, work here. Put your answer to B here, work here. C, over here. I swear to you, if your work is not done in this format, I am not going to grade it and I'm going to send it back. I'm telling you all right now, this is how I want this done. Listen to me. I will not grade an assignment that is not done in this format. Okay? No exception. I'm not going to waste my time. If you don't want to do it this way, that's your decision. My decision is not to grade it. So we have video evidence that I told you all that this is how I want this done. Anyway, so when you get to question number 5, it says, a force results in an acceleration A when acting on mass m, then tripling the mass and increasing the force 6-fold will result in an acceleration of. Okay? So we're going to base this idea of F equals ma. Now, in this assignment it talks about net forces. Net force is just what actually has to happen to cause an acceleration. So here's one of the most common misconceptions. Oh, every force causes an acceleration. It doesn't. This block of wood is sitting here on the table. Gravity is pulling down on it. The table is pushing up with an equal and opposite force. It's not accelerating. I've got this fan sitting here, okay? Gravity's pulling it down. Cable's pushing up on it. Now, however, I turn it on, okay? And then I let go of it. Then I get an acceleration, okay? But not until then. Now, and again, just because I turn on the fan, if I'm holding it in place, it doesn't accelerate. I let go of it, then it begins to accelerate. I stop it, no acceleration again. So just because something has a force acting on it, doesn't mean that it's going to accelerate. You have an imbalanced force, then you're going to get an acceleration. So an imbalanced force means the same thing as a net force. Okay, so let's talk about how you can do number 5. One option is that you do smash mouth physics, okay? And you make up numbers. And you go, okay, I'm going to take a 1 kilogram mass, excuse me, let me back up. I'm going to have a 1 kilogram mass. I'm going to make it accelerate at 1 meter per second squared. And that's going to require 1 Newton of force. Okay? Those are the numbers. Okay? You can use 5, 2, and 10. Doesn't make any difference. Let's just make it simple. So then you change the condition and you go, okay, I'm going to triple the mass. So that's going to become 3 kilograms. And then I'm going to increase the force 6-fold, which means that's going to become 6 newtons. So the only way this thing balances out is if my acceleration becomes 2 meters per second squared. So if you like smash mouth physics, where you put in numbers, here's how you would do this particular problem. If you want a more elegant approach, you go F equals ma. Then you go 6F, 3m, and again, to make everything balance out, my acceleration would have to become 2a. So I don't care how you do this problem. If you hate this concept and you like numbers, put in numbers and you'll see that the acceleration doubles. If you're more of an elegant mathematical kind of person, this increases 6F, mass goes up by 3, my acceleration would have to double to make everything balance out. So there's that. When you get to this question on number 9, if the net force is 0. So I showed this on the video that didn't get recorded, so let me show this again. So, hold on, there it is. Okay, so if I give this hockey puck a push, all right, it comes to rest because of friction, all right? So the only reason but here's what's important. The only reason that you ever have to apply a force to keep something moving is because of friction. If you remove the frictional force, inertia will keep it moving on its own. So if I turn on the machine, okay, and then let it go, you'll notice that it just keeps moving because of the fact that we have removed the frictional force. So one of the things I want you to get out of your minds right now is that you always have to apply a force to maintain motion. You have to apply a force to maintain motion if there is friction. If you remove friction, inertia will keep it moving on its own. Because remember, Mother Nature is a lazy prima donna. If you give Mother Nature a velocity vector, that's what it wants to keep. If you change that velocity vector by making it bigger, smaller, or changing the direction of it, that requires a force. Okay, so keep that in mind when you answer number 9. Okay, here's how you can use F equals ma. So let's say that you've got a car that's at rest, okay, and it's going to speed up to 10 meters per second. Mass is 2 kilograms, and that's going to take 5 seconds. Okay? So imagine that you've got a car like this, okay? Right? And you're going to turn on the fan. It's going to start from rest, and it's going to be going 10 meters per second. Mass is 2 kilograms, takes 5 seconds. So basically, you're going to use F equals ma, because I want to figure out how much force this is going to take. So this is why you have to be able to do acceleration equations before you do force equations, because we've got to be able to calculate that acceleration. Now, if you're fancy, you can go, oh, I know my initial velocity, I know my final velocity, and I know time. So I can go v minus v naught over time equals force. Oh, okay, so that's 2 kilograms. My final velocity is 10 meters per second minus 0 divided by 5 seconds. So this becomes 2 meters per second squared times 2 kilograms. I get 4 newtons. Okay? So if you can calculate the acceleration, and we talked about this in terms of the lab, if you can calculate that acceleration, multiply that by the mass, you can get your force. Now, the other side of it is that if you know that you have this car, right, and let's say the mass is 2 kilograms, and you know that you're going to have a net force acting on it of, I don't know, negative 20 newtons, and don't flip out on the negative. That doesn't mean the car is going backwards. It's just the magnitude of the force, and it's acting in the opposite direction of motion if it has a positive velocity. So if I can calculate my acceleration and go, oh, force net equals ma, divide by mass. So then if I take that negative 20 newtons and divide that by that mass of, what do we say, 2 kilograms, I get an acceleration of negative 10 meters per second squared. Now, what this means, that negative 10 meters per second squared, if here's your velocity time graph, it doesn't make any difference where you start. If your initial velocity is some positive value, that means you're going to be slowing down. There's your acceleration. That's the slope of your velocity time graph. If the object is at rest, that's going to be the slope, and it's going to speed up with a negative velocity. That doesn't mean it's going backwards. It just means it's going to have a negative velocity. If you're already starting with a negative velocity, and you have that negative acceleration, there's a fly, that just means that it's going to speed up. So get out of your minds that a negative net force means you're going to slow something down. You're only going to slow something down if you have a negative net force acting on something that has a positive velocity. If it's already moving with a negative velocity, that negative net force is just going to make it speed up. So get out of your minds the idea that a negative net force means that you're slowing down, or a negative acceleration means that you're slowing down. Okay. When you get to number 5, okay? When you get to number 5, problem number 5, I should say down here, here's the situation. You're pushing this block, okay? And you're pushing it along at a constant velocity of 5 meters per second. When in doubt, draw a picture that shows all the forces acting on this thing. So I'm pushing it along. Now, by virtue of the fact that I have to push it, implies that there's a frictional force. So I've got 3 forces, Fg, Fn, force applied, and force friction. Okay, those are my 4 forces. Now, you're told that the coefficient of friction, this is on problem number 5, you're told that mu is equal to 0.380. Now, remember, mu equals force friction over force normal. I'm trying to find the frictional force, because if I can find the frictional force, then I know how much applied force has to be exerted to balance that out. Now, remember, quick refresher. On a flat surface, force normal is the same as your gravitational pull, which is the same as mg. So, to get your normal force, you're going to take that mass, which is 4.80 kilograms, multiply that by g, that's going to get you your Fg, that's going to get you your normal force. So, on problem number 5, here's your mass, multiply it by g, get your normal force, that's the same as your Fg. Then you can multiply that by 0.38. Hey, now you can get your frictional force. What you need to decide in this problem, do you want your frictional force to be positive or negative? Let me give you a hint. Make it negative, because the block is moving with a positive velocity. that direction is positive. So the frictional force has to be acting in the opposite direction. Okay? Keep that in mind. Now, what's going to happen is that we're pushing this thing along and then we stop. Okay? We stop applying the force. Well, what happens is that you lose this applied force and you still have the frictional force acting in the opposite direction. So keep that in mind when you do no problem number 5. Other than that, there are some problems, some questions in the back of the book. When you get to problem 49 and 50, and I tell you this, it involves like a rocket. You're going to draw at least a couple of velocity vectors and an acceleration vector. So if it, like for example, if it's a rocket and it's speeding up, going up, then you go, oh, here's V1, here's V2, there's the direction of my acceleration. If the rocket is slowing down as it goes up, you would go, oh, there's V1, V2 is a smaller value, and then you'd have negative acceleration. So if you're watching this, this is just an explanation of assignment 4.1. So if you are on my Friday group, you need to work on this assignment tomorrow on Thursday. If you're on my Thursday group, don't worry about this. I'm going to give you this tomorrow, but you do need to watch this video at some point because it's going to help you out a lot. And if you already watched it at this point, then you already know that. Okay, kids, we're done. Great.